Srinivasan, any more people? Dr. Bala is there, KRB is there.
So Dr. Bala is here. Yes,
Yeah.
sir. Dr. Bala is sir, and Gayatri, Dr. Purva, Dr. Gayatri, all of them are there.
Okay. Sir, we'll just wait for another 2 minutes. Okay, I think we'll start. It's already 7. Yes, Vanilla is my PhD student, and she has worked on glucose in silico model, plasma glucose regulations. She has essentially, why this is important is because the physiology, actual physiology, uh, is converted into a mathematical model. How do you do this? This is the question. And then how do you solve it? Maybe that details may not be right now of interest, because that involves mathematics, and that's a black box. It doesn't matter. It's easy to do that. So then, how do you interpret this kind of model, and how do you make it into a patient-specific model, which is yet to complete it, but so that every patient can have a twin in the computer, a diabetic patient, a twin of him or her in the computer. How do we do this? So this is the whole thing. And Vanilla has done excellent work. She has worked on each of the mechanisms of physiology. And so over to you, Vanilla. Start.
Thank you very much, sir, for the brief introduction about my work. Very good evening to all the doctors presented here and all the researchers and other professors and everyone here. I welcome you all to my seminar talk. So, my name is Vanilla. I'm a student of Professor Krishna Kumar. So, here is my title, research PhD work research title as in silico model and sensitivity analysis of plasma glucose regulation towards an individualized maximal model of physiology as well as pathophysiology. So here are the brief overview of the seminar talk, whatever I'm going to present here. So introduction and the research gaps and motivation and some of the objectives and model formulation, as well as the clinical data which I have taken for validation, as well as results. So in the results I have done like mathematical model estimation as well as validation, and then sensitivity analysis, and then followed by summary and then references. So I'm going to take like 5 to 7 minutes hardly for introduction part alone, because it's very, very important to know about diabetes, more about diabetes. So especially diabetes is a life-killing disease, as you all know. It's a dangerous disease. So every 5 seconds, one person dies due to diabetes, as well as the complication of diabetes. Not only diabetes, the complication related to the diabetes. So every 5 seconds, one person is dying. So look at that. If you see the prevalence of morbidity and mortality, it's very ramping up over the year. So it's very crucial. Everybody has to understand and aware of this diabetes. So before going into diabetes, the pathophysiology, I just introduce the fundamentals of glucose metabolism. So what are the fundamentals, the basic foundation of glucose metabolism? So for the regulation of blood glucose in the blood, whatever the food we are taking, it has to be utilized. Whatever the energy we have consumed, it has to be utilized by the body cells. It should not be always there in the circulatory level. It should be utilized. So for regulating this glucose metabolite, there are many other hormones many other hormones are responsible for controlling this blood glucose. So hormones such as insulin, every good doctor and every patient having a diabetes are are very well known about insulin and glucagon hormone. Only the specific doctor and diabetologist and the other researchers are known doing the research under this area are well known about other key hormones which is like playing a big role in the diabetes. So, so before going into the pathophysiology, I'll just explain the brief introduction about the physiology. So once you consume the meal, it has to enter the stomach and then it is entering into the intestine, in the small intestine where the absorption of the nutrients happens. The nutrients which is, that carbohydrate, fat and proteins. The major amount of glucose or that is the energy fuel, right? That is comes from the carbohydrate. So 60 percentage of the energy fuel comes from the carbohydrate. So once the carbohydrate has been absorbed in the in the intestine, it is converted into glucose and enters into the plasma. So as soon as the glucose arrival in the plasma, there is a hormone in the intestine itself called incretins, which has two hormones, GLP-1 and GIP, which sends signal. It parallelly sends signal to the pancreas. The pancreas is the hormone which is located beneath the stomach. It has the numerous islet of Langerhans, numerous number of cells. Each cells having commonly three type of specific cells called alpha cells, beta cells, and delta cells. These alpha cells secrete glucagon hormone and beta cells secrete insulin hormone and delta cells secrete somatostatin hormone. These alpha cell and beta cells are very crucial for preventing this diabetes, preventing this excess glucose in the blood. So always this glucose and insulin has to be uh, equally balanced. Then only the glucose in the blood has to be regulated. So once the incretin hormone gives signal to the pancreas, beta cells, especially beta cells, to start secrete the insulin. Hey, this glucose occurs in the occurs in the plasma. So now do your job. You have to start secrete. Now insulin has been secreted. Then the plasma glucose has been utilized by the skeletal muscles. So this insulin, it has two jobs. Parallelly, it has two jobs in the normal person. One is it is helping for the glucose to utilized by the body muscle cells, as well as it will give signal to the liver and stop producing the endogenous glucose production. So parallelly it has it suppresses the liver production of glucose, as well as it is helpful for the muscle cells for uptaking the glucose in the plasma. Two jobs it has to do. So very crucial hormone, it has to do the two job. If any of the one job fails, then the person having the high level of glucose in the plasma. So parallelly, when the glucose level in the insulin level is high, in order to maintain the normal glucose, the glucagon hormone has to be low. As you see in the pancreas, the glucagon hormone which is secreted from the alpha cells, so it has to be low. Similarly, there are two hunger hormones always when you start eating the food, the glucose metabolism started right from that place itself. So when you are feeling hungry, there is a hormone which is secreted from the stomach called ghrelin, which gives signal to the brain that your stomach is empty, you have to start eating. So now you are eating. So once your stomach is full, the ghrelin will be reduced. The another hormone, which is counteracting hormone for ghrelin, which is secreted from the adipose tissue called leptin, which gives signal to the brain again that your stomach is full, now you have to stop secreting, now you have to stop eating. So these two hormones, it's the first phase of your glucose metabolism. So always the ghrelin and leptin has to be equally balanced. So other than this, there is a fatty acid contribution towards this normal glucose in the blood. So what does fatty acid do? So always similar to when you are doing the heavy over exercise or when you are fasting, so you have a very low level of glucose in your blood. So during that time, the free fatty acid comes to a place. So it is acting as a fuel for your energy. So the free fatty acid will be taken up by the body cells. So again, insulin will be responsible for the uptaking of fatty acid by the body cells. So this free fatty acid also what it will do, it will go and sit on your liver and form the glucose storage. So liver is the bag. It contains enormous amount of glucose has been stored. So whatever the other nutrients called protein as well as the free fatty acid, over the period of time when your glucose is high in the blood, so this free fatty acid and protein over the period of time, it is again converted into glucose and then it is again stored in the liver. So whenever we have the over exercise, when we are doing over muscular activity, this compensation has been taken place by the FFA and then proteins. So this is normally happening in any normal person. So for diabetic, here is the problem. Even when you have an enormous amount of blood glucose because of your meal consumption or glucose consumption, for glucose patient, this FFA is keep on stored in the liver and will the insulin, because of the lower secretion of insulin or because of the insulin inefficiency, the FFA is keep on converted into glucose and it will be accumulated in the plasma circulation. So this is basically happened. So all the responsible hormone has to be regulated in order to maintain the normal level, and the free fatty acid is again similar to glucose, acting as an energy source. It is also has to be regulated. So this is the basic physiology for any normal person. Any violation, okay. Now comes to the point called chronic hyperglycemia. So I figured out, I see this glucose whenever whenever I say diabetes, which means I refer like type 2 diabetes, because it is commonly 95% of people adult having type 2 diabetes than type 1 diabetes. So my main motivation of this is like major number of people are having type 2 diabetes. That's why I have taken this as a challenging task for my research. So here this excess glucose in the blood over the period of time, it leads to chronic hyperglycemia. So basically this monster is having this glucose monster, which means like glucose type 2 glucose diabetes, which is a group of metabolic disease, which is not a single disease, which is a group of metabolic disease which is having one common thread. The group of metabolic disease having one common thread, which is called chronic hyperglycemia. So this common thread having many death stones, each stone I refer to a different types of diabetes. So each stones. So in the figure, in the monster figure, so this is the death sting. This is the common thread. Each the thread having many number of different death stones. So here one extreme end, which will be like this hyperglycemia occurs because of two reasons. Mainly two reasons. One is insulin secretion is very less, or sometimes it is zero. Then other reason is insulin efficiency will be normal or more than that, but it is reduced action of insulin by the body cells. So which means like increased resistance of insulin action. So because of these two reasons, we have a chronic hyperglycemia. So in the one extreme case, type 1, one extreme case is the first death stone is type 1 case. So type 1 case hyperglycemia occurs because of less number of, which means like deficiency of insulin or no insulin at all, which occurs for the young people, like less than 35, less than 25 age people. This type 1 case occurs. Basically for young people, this type 1 case occurs. So because of less secretion or sometimes no secretion. So this is called type 1. The another extreme is type 2. Which is like increased resistance of insulin action. We have a normal secretion of insulin as well as more than normal secretion, but the action is not that good. The resistance is more for the insulin action. The body cells is not taken up by the secreted insulin. So that is the case of type 2. So during this case, the chronic hyperglycemia can occur. So other than that, only good doctors knows type 1 and type 2. The specialist or diabetologist and any independent researcher or other researchers knows other death stones based on these two conditions. The other death stones called LADA. LADA means latent autoimmune diabetes of adults, which this LADA is, it's like a type 1 disease, type 1 diabetes, but for the adult people. So for adult people, the beta cells has been destroyed over the period of some age. So for adult people, this type 1 diabetes will be occur. The sufficiency of insulin will be less, and then or sometimes the secretion, the beta cell has been destroyed. Because of that, LADA can occur. So because of it, it leads to chronic hyperglycemia. So another extreme, another type called MODI. MODI means like maturity onset of diabetes at young age. So it is like type 2 diabetes for young age people. Young age people. So the maturity onset of diabetes occurs, which is like more like at the initial stage, like very young age. So because of this, for the young age people, the sufficient insulin secretion will be high, but the resistance of insulin action will be more. So because of this condition of diabetic chronic hyperglycemia can occur. The other side, other type, other dystone.
Right,
So some people.
Fast, back to your thing, because time is a problem. No?
Yes, sir. So the other thing is similar to this type 1 and type 2. The other thing, if people are taken drug, any drug related to some other complications, over a period of time, the chronic hyperglycemia occurs. The other one is the gestational, because like for female, it is limited to only female, those who are under pregnancy. So these are the basically the different dystones occurs in the chronic hyperglycemia. Because of these two reasons, we have many other complications. So microvascular and macrovascular. Under this, we have many complications. So it's, as I said, like diabetes is a life-killing monster. So based on this as a motivation, I have took this as a challenging task, and I want, as an engineer, I wanted to mathematically form this physiology into an equation. So I took this physiology into a mathematical equations. So I have gone through the literature. Very few number of T2D diabetes papers are available in the research group. So these are the literature papers are majorly have like cited in under the diabetes field. So these are the main objectives. Like one is like first objective is like converting my physiology and pathophysiology of diabetes into a mathematical equations, and the equation has been formed. I have to validate the equation with the clinical data. Then only like I can able to estimate the significant parameters, which is each parameter having the physiological interpretations. So I can able to come up, say this is the parameter which is violating this particular regulation. So I have to validate the equations. Then after validating, since I have considered the key responsible hormone, the set of mathematical equation I have developed, which is like large in number, and the equation I have considered or large in number. So I have to reduce the complexity of my model. So in order to make my system like more reliable. So that's why I have gone through system analysis. So system analysis, what it will do, it will identify only the potential parameters which is impacting the model output, which is impacting the glucose, which is impacting the insulin. So that's why I have done sensitivity analysis of the model parameters. So these are the major objectives I have done. So as I said, I have converted the entire physiology into the equations. So first, these equations I have considered glucose. So glucose. So any equations I have formed here as basically governed by law of conservation of mass equations. So what the equation it will do? So the whatever the mass is will be conserved, which is comes input has been come and output has something has to be produced and something has to be utilized. So that's why the equation has to be balanced. So in this equation, the differential equation, the right hand side there are four terms. The first term, so if you see the figure here, it is easily understandable. So this is the blood vessel. Inside the blood vessel, the glucose has to be regulated. So the white dots are the blood glucose. How it is to be regulated? The production has to be regulated. Production has to be in the way, and the utilization of glucose has to be in a way so that the glucose has to be regulated. So the production term will be, where are the production terms? Where are the areas the production of glucose has been occurred? Glucagon dependent glucose production. So whenever the glucose is low in the circulation, glucagon has to be produced. Glucagon hormone, which is give signal to the liver to start secrete the stored glucose. So that is a one-way glucose has to be produced, and if excess FFA over a period of time, it is converted into glucose, and it is again increases the glucose production. So these are the two in glucose production. The external input which is contributing to this equation is the meal consumption. In the meal consumption, once you consume the meal, it enters into the stomach. There the grinding of meal occurs. If you have taken a food as a solid form, the grinding occurs. So in the stomach itself, we have a two phase, solid phase and liquid phase. The grinding of glucose occurs, and then it converts into liquid phase of glucose, and then it is enters into the intestine, where the absorption occurs, and then the rate of glucose appeared in the blood circulation. So this is the equations. Whatever figure I have mentioned here, that is equally represented by the equations in the left hand side. So first one equation is the glucose in the stomach solid phase, and second equation GSL is the glucose in the stomach in the liquid phase, and the third equation is glucose in the gut, and the fourth one is like rate of glucose appearance, which is in the equation rate KABS is the glucose absorption rate into the glucose produced comes from the gut organ divided by the body weight of the particular person. So this is the input RA of T, which is going into the glucose equation here. So that is the one equation. And then what are the ways it has been taken? One way, insulin independent and insulin dependent glucose uptake. So some
Vanilla, 1 minute, sorry to interrupt. Just
Yes,
go
sir.
back to the previous one.
Yes, sir.
So can you explain each term so that there are people who
Yes, sir.
familiar. So each term, what is G effective into
Yes.
GPFT? Yeah, like that.
Yes, sir. So the first term, which is the negative term, so this GAEFF is the parameter, which is like the physical interpretation of this parameter is glucose effectiveness. So glucose effectiveness is in the sense like there are some hormones which is like uptake, which is using this glucose without the help of insulin action. So organs such as brain and then kidney, these organs are not necessarily needed insulin as the uptake of glucose. So directly this insulin will be taken up by the particular organs. So this second term minus X of T into GP of T is the insulin independent glucose uptake. So for example, skeletal muscle and all the smooth muscles are using this energy like glucose, uptaking this glucose with the help of insulin. The third equation, which is the positive term, that means the glucose production term.
The second term is dependent. Yeah.
Yes, insulin dependent. The first term is insulin independent glucose utilization. The second term is insulin dependent glucose utilization, and third term is glucagon dependent glucose production. Because of glucagon, the glucose has been like sometimes like the glucose which is like very low in the circulation, so the glucagon hormone gives signal to the liver to start secreting the glucose in the plasma. So glucagon dependent glucose production, and the fourth term is FFA dependent glucose production, and the RA of T is the external input from the meal, the rate of glucose appearance, and the last term RE of T is the renal glucose excretion. So for a diabetic patients, the over a period of time the glucose will be secreted through urine, right? So in the urine the excess glucose has been secreted. So that is in this negative term because it is a secretion, so it is in the negative term. So this equation has been represented in the figure format here. So this first equation is in the mass of glucose mass. So I am calculating in clinically, if you take like glucose measured as the milligram per deciliter, usually the glucose concentration. So that's why the entire divided by entire volume of glucose distribution in the plasma. So G of T is the milligram per deciliter, which is clinically measurable. So all the X of T in the first glucose equation, this X of T, Y of T and Z of T, like insulin action, glucagon action and FFA action, everything will be again represented in equation form. So X of T is the insulin action. So in the figure, if you see plasma insulin produced produced from the pancreatic cell, and through the blood vessels, it is entered into the periphery where the receptors is occurring. The insulin go and sit there. So whenever the glucose comes, the insulin receptor will open, the insulin will go and sit to the receptor, and channel will be opened for the glucose, and glucose enter into the cells for the like further conversion of energy. So this is the action from the plasma to the insulin action that will be represented in the equation x of t, dx of t by dt. Similarly, glucagon y of t has been measured by the pancreatic beta alpha cell. So glucagon enters into the plasma, glucagon initially enters into the plasma blood vessel, and then it is go and sit on the receptors in the liver. There glucagon action will be carried out, and then production of glucose will be occurring. Similarly, z of t is the FFA action. So FFA, you know, like as I said, like it has two like actions. One, it is like uptaking the FFA by the help of insulin by the skeletal muscles, and the action which is like it is going to give sit on the like stored glucose in the liver, and start over a period of time it starts secreting the glucose production. So these are the actions which is involved in the plasma glucose. Similarly, insulin kinetics. How, like, what are the other hormones and what are the other factors which is contributing for the secretion of insulin? So we need to measure how much insulin has been secreted for this particular patient. If it's sufficiency or if it's insufficient. If it is sufficiency, then what is the problem? So there should be other causes, FFA, other reasons. If it is insufficiency, so okay, insulin is the problem. So for that we need to measure the insulin. So that physiology also has been converted into equations. So the first term in the IP of t equal to gamma 1 into G of t minus G threshold. The first term represents as soon as the glucose enters into the plasma, because of direct signal, the glucose directly gives signal to the pancreas, start secreting, hey, I have come here, please start secreting the insulin. So this is a direct signal to the pancreas over a threshold of glucose. If threshold like glucose will be like 70 to 100, 70 to 75, then the glucose doesn't need much amount of insulin for the uptake. So if it is more amount, like more than 80 or something, the insulin necessarily need insulin for the further uptake. So the direct signal of glucose to the pancreatic cell. And the second term, gamma 2 into F of t, is the FFA induced insulin secretion. So FFA induced, so similar to glucose, FFA is also in a substrate which is also gives signal to the pancreas, hey, I need insulin, so start secrete. So it is like FFA dependent insulin secretion. And the third term, so third term is a major term which no researchers has been contributed in this particular term. So it is called incretin hormone, which is like responsible 50% of insulin secretion has been carried out by the incretin hormone called GLP-1. So other than the glucose signal, direct glucose signal of insulin secretion, GLP-1, which means incretin hormone, that means like gut hormone, gives 50% contribution to the insulin secretion. So that is the numerator term, and denominator term 1 plus KLEP into L of t is the leptin hormone. So this leptin, L of t, and then exponential part H of t, these both are hunger hormones, leptin and ghrelin, which is both like inhibiting the action of insulin secretion. It has the inhibiting action on insulin secretion. So whenever insulin will be, whenever insulin will be high, this leptin and the ghrelin has to be low. So that is the term I wanted to mention here. So these both are inhibiting action on insulin secretion. Then minus term will be like it is like a basal value. So over a period of time, the insulin has to becomes to a basal range. So that is represented by the minus pi. It has to return to the basal value, right? So that is represented as the negative part of degradation, the insulin degradation. So again, this insulin is in the mass. I have to convert it into a picomole per liter. So which is like divided by the volume of insulin distribution in the plasma. So the same equation I have represented here in the figure format. So what are the ways insulin has been secreted, which is comes in, and what are the ways insulin has been degraded, and what are the effects inhibiting the insulin secretion. So these are the figure for the insulin kinetics. And the another one, glucagon hormone. So glucagon is the contracting hormone of insulin. So glucagon, so how when it is produced? When there is a lower amount of glucose in the plasma, the pancreatic beta cells send signals to the liver, glucagon sends signals to the liver to produce the stored glycogen. So always the glucose will be stored in the liver in the form of glycogen. So the glucagon gives signal to the liver to convert glycogen into glucose. So the glucose appears in the plasma in order to maintain the normal range. So this is the function of glucagon. So the first term, direct signal of glucose to the pancreatic alpha cell. The second term, so how the incretin GLP-1 gives signal to the pancreatic beta cell for the insulin secretion. The same incretin hormone, another hormone GIP, which is gives signal to the alpha cell for the secretion of glucagon. So the two incretin hormone give signal to the pancreas, one for insulin and one for glucagon. So that's why the numerator GI of T divided by 1 by GLP of 1. So this same incretin GLP-1, which is like inhibit the glucagon production. So both are GIP and GLP. One is for insulin secretion and one is for glucagon secretion. So that's and then exponential term of I of T. When you know, right, the glucagon, insulin is the counteracting hormone of glucagon. So whenever glucagon is produced, when because of the inhibition or reduced amount of insulin. So this insulin will be inhibiting the glucagon secretion. So what are the physiology way this glucagon has been produced? That is mathematically represented in an equation. The same will be like illustrated in the figure format. Similarly, FFA kinetics. What are the way FFA has been produced and what are the way FFA has been utilized? So FFA produced because of the lipolysis. So lipolysis occurs during the prolonged plasma glucose. Whenever you have the prolonged glucose in the circulation, the glucose over a period of time it is converted into a FFA. That process is called lipolysis. So that is the one reason FFA has been produced other than the direct consumption. So FFA has been utilized with the help of insulin as well as without help of insulin, similar to the glucose substrate. So like with the help of insulin, FFA uptake has been taken. This action has been given in the equation XIF of T. Similarly, insulin, like in the figure if you see, insulin has been produced from the pancreas, which is enters into the circulation and gives signals to and enters on the periphery receptors, and the insulin action on FFA has been carried out. So here anti-lipolytic effect has been carried out. Anti-lipolytic effect in the sense like uptake of it is protecting the FFA level in the it is protecting the FFA level means like over a period of glucose in the blood. So it is like FFA has been taken up by the muscle cells. So that's why the lipolysis process has been reversed. So incretin hormones. So as I said, incretins, the two hormones GIP-1 and GLP-1 and GIP. So both hormone has been secreted from the gut glucose. So after the intestinal glucose, it gives signal to the incretin, and then that is the factor which is giving input as the incretins, because incretin hormone also produced from the intestine, so that the hormone both the hormone gets signal from the gut glucose. So that is G gut of T minus, and the normal clearance in the basal clearance, it has to return to the basal level, so basal clearance. So for GIP of T also the input will be from the gut glucose. So both the hormones, the input is same, gut glucose. So that is represented in the figure format here. And then ghrelin and leptin hormones. So for ghrelin, what are the ways the ghrelin has been produced? The ghrelin, it is a hormone secreted from the stomach, as I said earlier. So it is not directly involved in the plasma glucose. It is it has an effect on the insulin. It has the effect on the insulin. Then from the insulin, the effect will be carried out towards plasma glucose. So there is no direct connection to the plasma glucose. Both the hunger hormone, even though both are hunger hormones, there is no direct connection. It has the effect on insulin, and then insulin will be correspondingly maintaining the plasma glucose. So the gut glucose, whenever there is an inhibition of gut glucose and then inhibition of insulin occurs, the ghrelin level will be always higher. So there is no direct secretion. Whenever insulin level, the ghrelin receptors identify there is a insulin level is low and there is a gut glucose level is low, then the ghrelin level will be higher. So that is the inhibition effect only. It will give signal. It will start secreting the ghrelin levels. So in the first two term will be the inhibition factor. That's why I will represent as the negative terms, and then last term will be a basal return. So at the end, no hormone will be goes to zero. Always it has to maintain in the basal range, even though whether you have a food or not. It has to be always in the basal range. That's why it is in the minus of HB. HB is a basal level. Any suffix like I have pointed out here is the basal value. Similarly, like leptin hormones, the leptin hormone leptin hormone secreted from the adipose tissue where the fatty acid will be stored. So the secretion of leptin is directly proportional to the free fatty acid. So that's why second term KH of T into F of T is the free fatty acid, because it's a directly proportional. So I have taken F of T as the one of the secreting factor. And then first term KL into I of T. So whenever the glucose like insulin will be higher, the leptin will be higher. So that's why I have considered in I of T insulin as a input factor, as a secreting factor. The last term minus P6 of into the again like the glucose has to comes to a return to a basal value. So that's why I have represented as a minus format. So like all the equations I have represented in a figure format in order to identify understand more easily. So these are the mathematical equation. These are the basic hormones I have considered for I have considered based on the physiology I have gone through for these many years. So for affecting the blood glucose. So that's why I have considered these hormones. So like I have to validate this glucose and insulin, and all the other hormones whatever I have considered here I have to validate, because all are differential equations I have considered. So I have to validate all the equations, and then only I can approximate the model whatever I have developed. But in India we have
1 minute,
yes,
just 1 minute. Sorry.
yes sir.
Is there any questions? Because you have put a lot of there are very many students. So if there are any questions, you can answer as far as the formulation of the problem is concerned. If there's any questions, there are people like Arjun, Dr. Arjun, who's extensive background in diabetes, and he's going to continue. So if there are any questions at this stage, I think it would be nice to answer, because then it will be easy for them to also remember and understand. Any questions?
Hello, sir.
Yes, please.
Hello, ma'am. First,
Yes,
I'd like to appreciate the work that you've done, ma'am. It's really new to see the entire body physiology as equations. It's an entirely new perspective on the entire field. I just have one doubt.
Yes, sir.
There was this formula that you'd used where the rate of absorption RA is equal to F. What is the F in that?
It's first that is a dimensionless parameter, sir. For it's like a constant value. For these equations whatever I have formulated, it is not like entirely I have written each and every time I have identified I have written. So there are pioneers, those who have already find out the basic equations for insulin and glucose dynamics. So these are the equations I have taken from the literature. This F corresponds to the dimensionless parameter in order to balance the equations.
Oh, okay.
Yeah,
Okay.
it's a fractional value. Yeah, it is a weighting factor. The real interpretation will comes under the KABS. It is a rate of glucose absorption. So the value of KBS is the physical meaning. Yeah.
And another doubt, there is a difference between the X of T and the rate of change of insulin, plasma insulin. That is.
Yes. If I of
How
T
is
is
that?
the yes sir. I of T is the plasma insulin, and X of T is the insulin action. So from the plasma, the glucose has been secreted from the pancreatic cell, and then it enters into the plasma. The plasma insulin go and sit on the receptors on the cells. Wherever the cell is there, it go and sit on the receptors. There is an action, insulin action will be carried out, right? So that action represents as a X of t. It is not direct plasma, it is a remote insulin. So plasma, it is not plasma insulin, it is a remote insulin, because during the signaling, the pathway of the insulin from the plasma to the cell, right? So there is a loss occurs. So directly the insulin action I can't taken as a I of t. The insulin action will be X of t, whatever is there in the happening in the cell area. So that's why X of t is differs from the, so the for X of t the input will be I of t, right? So the plasma insulin will be the input to the insulin action.
And the action depends on the insulin sensitivity, which is given by the parameter SI.
Yes, SI of t is the insulin sensitivity, which is the key parameter for many of the, for almost all the diabetic patients, this insulin sensitivity will be lower. So the insulin sensitivity as well as the glucagon effectiveness, GEAF, this is both parameters are lower for diabetic patients, type 2 diabetic patients. For normal patients, the value is higher than the diabetic patients. So the insulin sensitivity value will be lower, but for normal case it has to be a higher, because of the insulin resistance. This value is lower for the diabetic patients.
Okay.
Yes, sir.
Thank you.
Any other question? The only thing I just want to add is that many of them are proportionality constants. Like F is it's proportional to this, so we have a constant always. It's a proportionality constant. Yeah. Okay. No other question, please continue. Thank you. Please continue.
So in India, we have clinical data has been in clinically whichever the hospital diabetes related center we go, like only like.
It's my duty to thank Dr. Mohan from Mohan Diabetes. He has given us data, clinical data, to validate or see how best we can produce a digital patient. And so we have taken data from his hospital and then use that data in order to actually understand this mathematics behind this whole plasma.
Yes, sir. So it has been given like both diabetic patients data as well as normal patient data. So in order to see how my model is behaving, so this clinical data are very helpful. But as unfortunately only plasma glucose and insulin clinical data will be provided, because in India it is really unfortunate for clinically and ethically for measuring the other variables, other hormones called glucagon and hunger hormones and incretin hormones. But in Western and East Asian countries, people have doing their experimental stuff for measuring these particular hormones. So, but in India, plasma glucose and insulin widely it is measured in any clinical. So 48 normal case and then 105 type 2 case I have been taken. So this is the protocol which has been used here is extended OGT. So OGTT is the oral glucose tolerance test. So extended OGTT is like normally OGTT will be carried out over the period of 2 hours, but extended OGTT for 4 hours. So what is this exactly, this particular protocol? What they will do means after the entire overnight 8 hours of fasting, all the patients considered 49 and 102 diabetic patients, they will be the blood sample has been carried out in all the patients, and they all before taking the blood sample they are orally given 75 grams of oral glucose. So all the patients are giving the same amount of oral glucose, and then blood sample has been taken, and for the measurement of blood glucose and then blood insulin. So both the measurement has been taken out. So this is for normal case and then diabetic case. For first graph is glucose, plasma glucose. For the black line represent normal case, and then the red line will be a diabetic case. For as I said, for normal case, based on the initial peak. So look at the initial level at the time of 0. the amount of the oral consumption has been given. So before, this is a fasting. So at the time of 0, it is considered as the fasting period. So which is like assumed as the nothing has been given. They are in the fasting. After 8 period of fasting, they are not, they did not have any meal. So at the 0th time, at the fasting period itself, the glucose value is higher for the diabetic case. It is like as I said, like the normal range will be like 70 to 100. In some case it will be like 110. So if it is more than 110 for fasting, it is higher. They are like prone for pre-diabetes, and then over a period of time type 2 diabetes. So that is the for for T2D, for diabetic case, the fasting itself like higher. But the initial peak occurs for normal case, it occurs at the time of like 40, around 35 or 40. But normal, look at the graph of diabetic case, the initial peak occurs at the time of 70. This delay, this delay occurs due to very slower movement of the stomach emptying. The food whatever you have consumed, or glucose whatever you have orally taken, the emptying of the food or emptying of the glucose from the stomach, that is the process, the movement is will be slower for the type 2 case. There are still, the reason it is still uncertain, but the movement is slower for the type 2 case. That is the reason for the delay of peak value in type 2 case. And then once it starts secreted, once the peak value occurs, the insulin, as I said, the physiology, the insulin will be secreted. So correspondingly, look at the graph of insulin, for the normal case and then type 2 case. Based on type, here the type 2 case insulin is more sufficient. It is like, it's not, there is no insufficiency, it's more sufficient. So insulin is there, but even though insulin is there, plasma glucose is higher. So look at after a basal period, after 200th time, like 200th minute, the glucose comes down, but it not goes to the basal value. It is there in the around like some 90 or in the range. So where is the problem? Insulin secretion is there, but glucose is always higher. So this kind of patient, diabetes having resistance, increased resistance, insulin resistance. There is increased insulin resistance. That is the case we have come across here.
Can you also explain, for example, just go back. So you have so many parameters.
Yes, sir. This is the clinical data. So model simulation, it comes comes in the later side, sir. It's a clinical data. Whatever I got it from the Dr. Morgan Diabetic Center. I just got averaged. This is average of normal and diabetic patients' data of glucose and insulin. So this is hereafter the model estimation comes here. So RA. So again, black RA. This is the graph of RA, not plasma glucose. This is rate of glucose appearance. At each rate, what is the glucose appearing in the plasma? That is the rate, milligram per kilogram per minute. What is the per minute glucose is occurring? So that is captured in the RA. So this black is the normal graph, and the red is the type 2 graph. So look at the graph. The RA is both, like here RA is for diabetic case, RA is less. If you see the peak value, the RA is less. So but diabetic plasma glucose is higher, right? See, look at the graph here. So RA is the one of the input term for the G of T, right? But RA is for diabetic case, RA value is less compared to the normal case. But glucose graph, like for glucose, the plasma glucose for diabetic case, it is higher. This particular load, this almost it is are equal. When you look at the area of the entire exertion, the area under the curve for both normal and diabetic, it's not varied much. Both are significantly equal, I can say. So RA, it's one of the input factor. The area for both normal and diabetic case is almost equal. So here G of T, as we this G of T and I of T has been validated. The solid line, or like our model estimation, and then the square and the circle or clinical data, and the bar which I have represented here as the standard deviation of the clinical data. So the black line, see this all the clinical data, the model is exactly approximated the clinical data which has been used here. So here, look at the patient data, the diabetic data. It is tremendously high. As I said, like even the fasting, postprandial glucose, postprandial consumption of meal, when you measure the blood glucose, it has to be less than 150, not beyond 150. But here the peak value is almost equal to 250. The severity of type 2 diabetes is higher for this particular patient. So correspondingly, the insulin plasma insulin graph, if you look at the graph, the type 2 graph will be very higher. So here the increased amount of resistance, insulin resistance occurs. Because of that, plasma glucose is higher for the particular diabetic patients. So when you look at the area under the curve, it is double the amount of normal. The entire 244 hours, this is extended OGT, right? So 4 hours of measurement has been carried out at different instant of time. The entire area glucose exertion, if you capture, see, the normal is compared to the normal, T2D is double the amount of double the amount, right? So it is like the severity of diabetes is very severe for the considered patient. So as I said, in the insulin equations, there is a one is the direct signal to the pancreas.
Just
Yeah.
just a minute.
Yes,
Just
sir.
go back to the previous
Yes,
one.
sir.
Just tell
Yes, sir.
the audience, how did you get? There are so many parameters. That's what just I was asking you. There are so many parameters in these equations,
Yes, sir.
right? So you have to estimate these parameters.
Yes, sir.
There were, like, for example, parameters which have to do with the
Yes,
uh,
sir.
ghrelin, then incretin, then GLP-1. That is, in other words, GLP-1, CIT,
Yeah.
and
Yes,
all that.
exactly.
So you have so
Yeah.
many parameters which are with respect to these incretin hormones, ghrelin, leptin, and so on. So how did you evaluate these constants so that your graph, which is mathematically modeled graph, that red and that solid lines, they sort of very well coincide with the patient data. So how did you evaluate those things to get this kind of nice graphs? Can you just give
Yes,
a,
sir.
no, I know it is very involved, but just give a,
Yes,
oh,
yes, exactly, sir. Whatever you said is correct.
yeah,
So, yeah, like for plasma glucose and plasma insulin, clinically I have a data in hand, which is like which is directly come from the clinic. So I have like used that data for the validation of the corresponding equation of glucose and insulin. For the other equations also, I have to parallelly validate because to estimate the parameters. So these 15 equations, whatever the equations variables I have considered, we have a 15 equations. So similarly, like 50 for this 15 equations, I have 41 kinetic parameters. So 41 parameter rate constants I have. So for this rate constant, some of the rate constants or some of the terms in the equations I have like utilized from the pioneers for the previous group people have done the research in the same area. So what are the terms physiologically considered here, physiologically have introduced here? For this particular term, I have assigned the range for the particular parameters. So these are the rate constant parameter for the physiological range. As for biology, any physiology parameter which will not go negative value. So always it is in the positive area. So that is the one constraint I kept it here. So I have kept a range for the particular parameters, whatever I have included here in these equations, and then I have estimated all the parameters. The parameters which I have taken from the literatures and parameters which are whatever I have considered, all the parameters I have estimated and then validated. The other equations, the other hormones like ghrelin, as I said, like ghrelin, leptin, and then uh, ghrelin, leptin, glucagon, and other variables and other hormones. I don't have a clinical data. So, but I need a data to validate, right, to approximate my model. So I have taken the literature, the theoretical people have done in the Western countries. Each paper they have done different studies. Suppose in one research group they have done only the glucose research. They have done an experimental study and they have measured the glucose under a OGTT condition protocol, and then they carried out the measurement for a different instant of time for 240 minutes. So I found out the literature's data for glucagon and hunger hormones and incretin hormones. So each paper, I have different papers for different data. So but everybody, all the data I have gathered here for type 2 case only, not from type 1 case, because yeah, the criteria, the situation, everything will be vary, but it's like unfortunate to having a data here, clinically measuring the data here. It's unfortunate in India, but it's not easily possible. So that's why I've taken a literature survey data for the other variables, other hormones, whatever I have considered, and I have used that data for the approximation and parameter estimations. So in these equations, I have 41 parameters. So 41 kinetic parameters. So
So let me summarize.
yes, sir.
Which means that you have taken data published by others,
Yes.
and then estimated the range of each of these things. So ghrelin, they measured it, leptin, and all that. So you estimated the range, and so that you know what can be the range in an individual physiologically, acceptable range. And with this range, you went back to your equations and then did a parameter estimation with the OGTT and results that you have from the patient. So in other words, you have estimated a range and then or found out a range and then estimated. Okay, right? That's
Yes, sir. So what I have done is I have taken the literature's whatever the parameter I have taken from the literatures, I have taken the particular value, and because I don't know the range about the particular value, because they have already optimized that parameter. So I have taken that parameter as it is. So whatever I have considered the terms in the equations, that parameters I have kept a range. Um, and then I have estimated the optimal value. So I have given a lower bound and upper bound for normal case and diabetic case. So, and then the optimal parameter for normal as well as diabetic case will be measured based on the validation, model fitting. In simple words, I can say for model fitting, clinical data, for clinical data, and then whatever model approximated, both has been fitted and the parameter has been optimized. So this is the way I have optimized the parameter for normal case as well as diabetic case. Not exactly the range I estimated. That value, the range I have given, I don't know the upper bound. What is the last value of the upper bound? I really don't know for the normal case as well as diabetic case. I have given the range, but some of the values from the diabetic case in the range, which will be comes under the normal case. So it's not like exactly the range is different for normal case as well as diabetic case. That estimation has to be carried out in future. But here the range I have been given, and then the parameter value has been estimated for the different case, normal as well as diabetic case. So this is what I have done. So these are like everyone can able to see the parameters table here.
no, the parameter table is not visible. So there's a lot of parameters. So ultimately, what essentially, just to summarize, so each patient you have produced a digital twin in the computer by estimating their parameters.
Yeah.
Let's say that.
Yes, sir. Yes, sir. I have given the bounds, lower bound for estimation itself. I have given the bounds for normal case as well as diabetic case, lower bound as well as upper bound for normal, and then for diabetic, lower bound, upper bound, and estimated the particular optimal value. So with that particular value, my model approximation is fitted with the clinical data.
Okay.
Yes, sir.
Yeah.
But the parameter is varied for patient to patient. For this particular patient, this is a parameter. For if suppose in future one other patient comes, one other test patient comes, the parameter will vary based on according to the profile and clinical data. The profile will vary. Correspondingly, parameter will be also vary. So this is a graph of insulin without consideration of glucose and without consideration of insulin incretin hormone, considering both in glucose and GLP-1. So my clinical data exactly fit with the model equation considering both GLP-1 and then glucose. So if this graph exactly showing the importance of GLP-1. If I ignore the GLP-1 term in the insulin equation, I'm not able to produce, I'm not able to get exactly the clinical data. My model simulation is not exactly fit with the clinical data. So when I'm ignoring the glucose part, considering only the incretin induced insulin secretion, even then that time also I'm not able to reproduce the exact clinical data. So when I'm considering both, I can able to represent the clinical data. So when developing a model, it is very important to it is always very important to trade off between model complexity and fitting it has to exactly behave the glucose dynamics. We have to represent the glucose dynamics as well as the complexity also be lesser. So that trade-off has to be equal. So reducing the parameter, if I keep on reducing the parameter, if dynamics is matching, like my model approximation and then validation clinical data is approximated, then it's fine. But reducing the parameter which is not, but the dynamics is vary, the fitting is not possible, then that is not a good model. So you have to always be in a trade-off between both complexity and the model capturing of model dynamics. So in that case, look at this can be measured by the criteria called AIC criteria, Akaike information criteria, which will give you the value, the which model has less value of AIC has more desirable. That model is more desirable. So when considering the both three cases, glucose only, GLP only, and both glucose and GLP-1 consideration, I have a less value of AIC in the considering both value of both functions of glucose and GLP-1. So this is one like just to just to just to understand how important the each terms, each parameters in the model equations. If we ignore one physiological function, if you ignore one physiology for the particular variable, so that is really like impacting the dynamics of the system. So that is what it is like representing in this particular slide. Similarly, like this graph particularly for glucagon and then FFA. So as I said, like whenever plasma insulin is higher, that time glucose has to be reduced. Glucagon has to be lower value, because insulin and glucagon both are counteracting hormone. When insulin is higher, glucagon has to be lower. So as I said, the glucagon after the consumption of meal, from the initial value it is comes down, and over a period of time it starts increasing. So you can correlate with you always like correlate whatever the variable, whatever the hormone plots I have mentioned here, you can correlate with the plasma glucose, which because of this reduced level of glucagon in the what to say, like insulin value will be higher, and then correspondingly plasma glucose value will be higher. So for normal case, for diabetic case, look at the diabetic curve for glucagon, it is higher, right? So for it is also higher. So the diabetic glucose we have seen it is very higher, right? So one of the reason is glucagon over secretion of glucagon in the diabetic case, it is like impacting on the plasma glucose diabetic case. So it is we always like correlating each graph with the glucose value.
Vanilla, you have to point out that this data is different. This is from.
Yes, this data is different, but the physiological range for diabetic and normal is like it is like yeah.
I think you have to move forward because I think time.
Yes,
So,
yes.
so in other words, you are now showing how you evaluated the range by taking data from the literature and fitting it so that you know the range in which each of those parameters vary, and that is what is used for individual persons fitting the.
Exactly, sir. Exactly.
So just
Yes.
sorry to interrupt. I'm very sorry that I have
No, sir. Yes, sir.
time. So just because this a lot of work has gone into this, but I just wanted to summarize in a couple of statements what has been done so that people understand it. You go to this.
So similarly, like the other hormones which is clinically not possible in India, the other hormones, the literature data has been taken from the research study, and then the model has been validated. So just to approximate the model, like so we know the physiological range. We are not entirely deviating, even though the real patient comes. If we measure the ghrelin and leptin, it is always under the physiological range. It is not going beyond the range. So I have, in that gut feeling, I have taken the literature data and approximated all the equations. So here it has a 41 parameters. I told you each parameter having a physiological interpretations, but all the physiological interpretations, is it really impacting my model output? That is the question mark here. So that's why I went into the sensitivity analysis. Is it all the 41 parameter I need to estimate all the time? So that's why the sensitivity analysis will give you the answer. What are the important factor, or what are the significant factor which is affecting the glucose output or affecting the output, whatever we have considered here. So this I have done in Python, like sensitivity analysis library Python Salib, and I have initially, like with the 20 folds of parameters, I have initially defined the parameters, 41 parameters, and then given the range, and sorry, not range, I have given the 20 folds of lower bound and upper bound with 1000 number of samples. So with that, I have wanted to find out the first order, total, second order, and total order indices. So each, these are the metrics, like first order, the output of the sensitivity analysis, particularly called Sobel method. This method is very efficient method when compared to other sensitivity analysis method like Morris, and then fast algorithm or something. Like Sobel has a very efficient method which is exactly identifying the significant parameters, which other methods which is like neglecting it. So but this method has a complexity of computational cost. So I have waited for, literally for one case, I have waited for one whole day, 23 hours I have waited for the 84,000 model simulations. So for, because like 84 like for 24,000 samples I have considered, so 84 model runs has been carried out. So because each parameter having 84,000 values, so 41,000 parameters, sorry, 41 parameters into 84,000, each parameter having 84,000 values. Then the model has been validated, model has been evaluated for these each 84,000 times, and then the time series of glucose, whatever the output variable I have considered all the variables here as an output variable at each point of time. So glucose has been considered as the output at first point of time, like the time series of glucose has been like converted into a metric of I have taken a single values out of this time series of plasma glucose, because it is a time series, but the input I have given to the sensitivity analysis one single values. I have taken a time, maximum time at which the peak glucose glucose peak value occurs. That is a metric I have taken here, and then I have find out all the metric maximum time peak value at what time it has been carried out. That I have taken for all the 84,000 glucose value, and then that it has been fed back to the sensitivity analysis, and then able to find out three metrics: first order, second order, and total order metrics. The first order metrics which give you this is the graph of first order and total order of all the 41 parameters. So the first order metrics which will give you the effect of this particular parameter towards the model output. Toward here it's a plasma glucose. So GFF here, if you see, the first highest contributing parameter, significant parameter is SF. SF is nothing but FFA effectiveness, FFA sensitivity, FFA sensitivity. FFA sensitivity, which means like the FFA action of glucose production, right? FFA dependent glucose production. So that is represented by the SF. So that is the first hormone which is which is having a higher potential, which is impacting the model output, which means like plasma glucose. The second next now dominant one is SI, insulin sensitivity. So action of insulin on glucose production. So insulin, it's very obvious, right? I can able to correlate physiologically with the each parameter how it is impacting. So the physiological interpretation, and then the mere logical assumptions and everything, like I can able to match with the particular table, like particular graph from the first order and total order effect. From the first order effect, I can able to tell you what is the particular parameter impacting the plasma glucose but the total order effect will give you, including the first order, what are the other interaction this particular hormone which is happening, all the interaction which is involved in the particular hormone, that will give you the total order effect. So other thing is that this is for plasma glucose. So for plasma glucose, only like approximately 10 or 12 parameters out of 41 are significant. So remaining parameter are almost negligible. So considering the plasma insulin as the output, so around here like some 13 or 12 parameters are significant, others are negligible. So if you see the highest parameter here in the case is gamma 1. So gamma 1 is which is the physical interpretation of gamma 1 is the direct impact, the glucose direct impact of insulin secretion. That is the gamma 1. If you see the G third from gamma 1 to third parameter G K underscore IGLP, that is the parameter for incretin GLP-1 hormone, which is also higher. So if we keep a hand on this particular two parameter, my model output is tremendously changing. So that is what we can infer from this particular graph. So what is the most influential parameters out of parameters for the particular plasma insulin? Here, these are the influential parameter. If we remaining all the parameters are negligible, we can fix all the other parameters. Only playing around with these particular parameters, we can see the dynamics of plasma glucose or plasma insulin, how it is changing. So the second order effect will give you the interactions. So some parameters, if you see some of the parameters are most parameters are negligible here, right? So from this you should not come to a conclusion, okay, these are the negligible parameter, I can keep it as a constant or fix it as some value or something. So we should not come to that conclusions. Some parameter which is negligible in first order and total order, it has an interaction with other value, other parameter and gives an impact. It is not directly impacting the plasma glucose or plasma insulin, which is like indirectly impacting the plasma glucose, which is playing with another parameter and then impact the plasma glucose dynamics. So that is captured from the second order sensitivity analysis. So when you look at the first plot of heat map, so the box located circled by the red color, which is the P1, the pair P1, the x-axis SI and y-axis P1. So this is the parameter, this is the pair which is interplaying the major interactions. So SI is the insulin sensitivity and P1 is the remote insulin action disappearance. So this as a pair, both here the P1 and if you capture P1 from the glucose, if you see the SI and P1, both having influence on the output, and that is represented here as a pair. It is represented here, and if you look at the oval shape I have circled in the black color, which is having a interactions. There is an relatively moderate interaction within this parameter. There are some parameters which has the interactions among themselves. That is also having a changes over the dynamics of the plasma glucose. So this this interaction effect can which I tabulated here, the first one is dominant P1 and SI as the pair, which is dominating, the interaction will be 0.05. So other subsequently the other pair which is like one step down, so which is affecting the plasma glucose with the interaction form, the one parameter playing with another, having a role on other parameter in order to affect the plasma glucose. So that is the thing which is I wanted to elaborate here. So similarly, the second part is like for plasma glucose, I have considered here plasma insulin as output and measured the first order indices, second order indices, and then total order indices, and corresponding the parameter pair which has an interaction effect. As a pair, this has an interaction effect. So which pair has the dominant interactions?
So that sum up because it's getting a bit late.
So similarly, yeah, as I said, like similarly, like so clinically, plasma glucose and plasma insulin. If you go to a hospital, any diabetic patient goes to a hospital, clinically plasma glucose and insulin has been measured. That will be considered as the output So if you measure OGTT test, plasma glucose will be the output. So plasma glucose, what are the parameter impacting the plasma glucose? That is the major thing. But here as a study, this is the elaborative study of diabetes, type 2 diabetes. I have considered each variable as a model output and identified what are the sensitivity parameters for each variable. So in order to, I don't want to neglect for some of the parameters from the ghrelin and leptin, which is not directly impacting the glucose. So in that idea, I should not ignore, but it is impacting the ghrelin, and ghrelin is impacting insulin. That's why I have considered all as the variables and then found out the significant parameters. So these are the output for other variables or other hormones which I have considered here and plotted what are the secondary interaction pair which is impacting the particular model output. Yeah, finally the summary. So what I have done, like I have successfully, like what are the model I have developed based on the physiology consideration. I have able to validate everything. I have able to validate with the literature data and the clinical data available, and then identifying the physiologically influential parameter towards the model output, which is directly affecting the model output. And then this particular research study is one step helpful for the future studies, like future type 2 diabetic research, because this model whatever I have developed, I can't say this is more realistic and reliable model. Every model is one step ahead from the previous one. So this model will be the one diagnostic tool for identifying the progression of diabetes, type 2 diabetes, as well as the what is the exact cause for the pathology of type 2 diabetes. In order, because we not necessarily depend on only on the insulin secretion is enough. Where is the exact problem? Is there a contribution of a glucagon or FFA? Where is the exact problem? So from this model identifications, we can able to represent very able to identify what is the exact cause for this particular pathology. So these are the conclusion I have came across from after the results part analysis and model validation and sensitivity analysis. So my model on my approximation and whatever study research work I have done here, which will be like in future, it will be like really helpful for the developing digital twin as for any particular patient they want a twin for them. They have we can use this model as a one step ahead as for the benefit of them, and then it will be for like very helpful for the precision medicine. For each personalized medicine, this model as one of the diagnostics tool, as I can say. So developing this particular model is a really challenging one because the physiology is very uncertain and complex. So that's why I took this as a challenging task. I have done a research work on type 2 diabetes.
So,
So
in other words, just to uh, briefly tell is that now she has identified what are the parameters which are important uh, in looking at all the results. So if you want to, so there are other parameters which doesn't have so much of effect. So now that she has about 12 parameters from 41, the 12 parameters have to be identified for a patient. If that is done, then she can build a digital twin, and that's the next step she's doing. She'll finish this next 1 month. So, is there any questions?
yeah, I welcome all your questions and feedback for my further improvement, please.
I have a doubt, sir. How are these equations how are these equations generally framed? Is it based on clinic? Because here we know that there's an inverse relationship between insulin secretion and ghrelin concentration. We could have just expressed this as is equal to 1 by some parameter times h of t. But then why are we choosing it as an exponential function? Is it based on previous studies that were done?
Exactly. This particular part of ghrelin involved in the insulin secretion is I have taken from the previous study, because they have used this particular term. They have put represented in a way of like Michaelis-Menten equations. So because it's an inhibiting factor, they are not directly like making it as a negative part. So they club together of insulin, ghrelin, leptin in the negative term. Yeah.
And I'm trying to understand how they actually come up with these equations. They take the clinical data, plot it in a graph, and from that they try to estimate which would be the best function to represent that data.
Yes.
Or okay.
Yes, because like if I ignore if ignore the exponential part of ghrelin, I'm or I keep it as a minus part instead of exponential term. I keep it as a negative term of ghrelin. I'm not able to approximate my model. Like I'm not able to validate my model. Like so that exponential curve. If I keep it as an exponential curve, I can able to approximate. So there are ways. So as I again I'm telling you, like this particular, I know this is exactly matching with the physiology. That's why I don't want to ignore this particular ghrelin part in the insulin equation. So that's why I've exactly taken from the literature.
Uh, just to add, Michaelis-Menten kinetics is very common in biochemistry. You know that. So this equation is very common in all the biochemistry studies when you look at enzyme kinetics. So the only thing that will vary from one to the other are these constants that are sitting there. But apart from this, the form of the equation is is very similar in most of the enzyme kinetic studies. In fact, Arjun, the book I have forwarded to you, you would find that in many, see, this is used extensively for PKPD models. All those things use this kind of form of the equation.
Oh, okay, sir. Yes.
Yeah. Any other question? Yeah. Okay. Thank you, Vanilla, for a very lovely presentation. Thank you very much. Thanks all of you for listening. Yes, it is a very difficult topic. A lot of things are there, and she has done an excellent work, and I really appreciate Vanilla for this work. Thanks all of you.
Thank you. I really thank you, my professor, for being a continuous supportive for till now. Like whatever the research I have undergone, there are times I have like left down. Like so, he's the one who pushed me that continue this work, finish this work. This is a difficult work, challenging work. So with the help of his continuous support only, I can able to sit and talk in front of you all and elaborate and explain my work. So thank you, my professor.
Thanks a lot. That's too much for me, but all things was done for you. Thank you.
Thank you, sir. Thank you for attending everyone.
Thank you.
Thank you.
Thank you, ma'am. Thank you.